last lecture this year, and today it's my real pleasure, to introduce a colleague of ours, a colleague of many of you as well, Ken Manders. So Ken, as probably all of you, or at least most of you know, has done all his career at Speed, which was something I learned, which I didn't know, that he started in the math department. Is that right?
Group in Logic and Methodology of Science.
All right. Before he was hired by the philosophy department a few years after having started in the math department. He's mostly known for his work in the philosophy of mathematics, and one of his most influential papers was written in 1995, but only published in 2008. But nonetheless has been read widely before getting published, and has created its own literature. The paper, some of you may know that paper. It's called the Euclidean diagram. So it's a word which is not friendly to French speakers. In any case, and what he told me also, and which I didn't know, is that he's got a lot of unpublished work on Descartes. So maybe 20 years from now, there will be a set of foundational papers which are going to create their own literature. So we're waiting to read these papers. But today it's going to be not on Descartes, but on the philosophy of mathematics, expressive means, and intelligibility. Okay.
Thank you. Thank you. Yeah, so I really think about understanding. It seems to me that is what, with ethical questions, those are the two traditional core philosophical topics. In the most recent century, a lot of people have avoided thinking directly about understanding, but here we are. You certainly have to find some way of making it a philosophical topic. That isn't perhaps straightforward. My examples are all from mathematics. But the lessons strike me as much more broadly applicable. Anyhow, you'll be the judge of that. So it's really intellectual understanding that I'm concerned with, intellectual contributions. And so the version of what is knowledge that I'm interested in is what makes intellectual contributions be valuable. And the terminology I'm going to use for that is that of intelligibility enhancement, enhancing intelligibility. You have some messy situation, you find the right intellectual way of approaching the topic, making it into an intellectual topic, and now it becomes much more intelligible. That seems to me historically and still today to be a really important phenomenon. And so the question is what's going on there. From my studies, I've isolated one aspect of what's going on there, the contribution of expressive usages that are introduced in the intellectual process. So I'm not saying that's the whole story, but it's what I figured I see a little bit about. Now, this is the outline. I did something like this in a week intensive lecture series a few years ago. So I take it you're not staying around for that today. But I've since then been working at cutting it down. There's a tiny initial example, the first case study, where I draw out only quite a simple feature, just to get us in tune. There are some foundational issues on how notation can matter that I'll address in terms of the notion of a functional role. And then there are, in principle, 3 application areas where I'm going to be surveying various mathematical developments that illustrate how specific choices of expressive means allow us to control levels of detail and how that is intelligibility enhancing, how they allow us to decompose into subtasks, modes, and stages. And in principle, there's another feature, namely how you structure your search space. That is still the Wild West. And so that part of the week-long series I had to simply cut today. And at least that's a good excuse. Okay, so my first case study now, there's a good deal more math up here because I want to, then is going to be relevant to getting the point I'm using it for today. So don't let that worry you, and I am going to have to go rather quickly. But there is this famous issue, the quadratic reciprocity theorem, proven by Gauss after discovery of a phenomenon by Fermat in the 17th century, and formulation of a proper conjecture by Euler in the 18th. There are now over 200 registered proofs by the German authority on such matters, and and there's much more work that's way beyond that, that is a leading strand in contemporary number theory, and without which, say, Fermat's last theorem would not have been proved, etc. So it is a major strand, though we're only looking at the very beginning. But the idea is that there's something very deep hidden, though the phenomenon is quite close to the surface. If you know about arithmetic modulo q, then one gets a notion of a square mod q. And so if q is 13, then 1 and 14 and 27 and 40 are squares mod q because they agree up to multiples of 13 with 1, which is a square. The same for 4, 9, 16, 25. That produces a collection. And in fact, these are essentially half the integers modulo 13, and the other half are non-squares. And so those go in progressions mod 13. Those are these progressions. And so we have this concept we can ask given 2 primes. I'm interested in it for 2 primes. Is P a square modulo Q? And if we fix the Q, then we can read it off from this table because so there's this finite computation here. And then you just look in these sequences mod 13, add 13 every time, and you look for the primes, and those are the answers. And so this initial finite computation has settled the matter. And it's, in some sense, periodic mod 13, except that some of the items in such a sequence mod 13 refuse to be prime. That's their problem. That was if we fixed the modulus, then we saw the easy problem. Now the thing that Fermat did is he had reasons to fix the prime and vary the modulus. And now, if I'm interested in the modulus 13, I can do what I did before. And if I'm interested in the modulus 5, I can do what I did before. But I have this computation for every expleted, deleted prime. It's not a finite computation anymore. But that isn't really the problem. But here are some results. Okay, and this is where this is the first point. What that actually matters for the intelligibility consideration, the one that I'm picking out of this large case study just for use now. We can do those computations. We can get the answers. How you like them? You don't see the pattern yet? You want more data? Great, huh? So one famous mathematician wrote about this at some point, not about this example, but though he's a geometer, he's commenting on a number theoretic thing. You get a computer and you know, it used to be hard to find out what the primes were, and now you just say, yeah, you just tell Mathematica to tell you what the first 700 primes are, and there they are before you get your finger off the key, enter key. And then you find it isn't what you wanted. And what mathematicians then say is, what people want is understanding. Well, so we need intelligibility enhancement. This is the starting. This is what makes us want intelligibility enhancement. We didn't have a question, for example, say, well, you know, so I didn't do 13 here, but you know, we could go back to it. We didn't have a question about, say, 53. This is finite computation, and then you run into that as a prime, and okay, you got it. And you also have an overall picture. Okay, anything in these 6 sequences that's prime is going to be 1, and the rest won't be. Okay, so you have a kind of satisfying understanding, whatever. I rearranged the big data. Actually, this is less than was on the first overhead, where there were less than 2 lines. This is a line and a half of the data put in a table. I know that mod 28, say 2 and nothing that's even is going to be a prime. So I didn't put those columns in. Nothing that's divisible by 7 is going to be a prime, so I put dashes in those columns. And now, in the other columns, I put either a dot or a 3 times 19 to indicate those things are not prime, but occasionally things in these columns are prime. Where 7 is a square mod that prime q, I made it bold, and otherwise I made it smaller and lighter. Okay? No, I've explained every graphical trick. Well, how do you like my table? Don't look at me, look at the table. So if this is representative, what's going on with quadratic reciprocity? Come on. If it isn't obvious, I'm going to have to leave. Have you looked at the table column-wise?
Some columns have no primes in them, or have no bolded numbers in them.
That's right. And the columns that have bolded numbers in them?
They're all bolded.
Yeah, it's column-wise, folks. Which means that this data has a period of 28. except that mod 28, a whole bunch of things refuse to be primes, their own problem. Okay, this table is also really the only way I know to explain what one would mean by something, a phenomenon being periodic, say with period 28, up to the aperiodicity of primes. To the extent that these items in these periodic structure are primes, they are squares mod 7. 7 is a square mod them, sorry. Okay? Well, so your response was not encouraging to me. The point was supposed to be that the table brings something out and makes it available to us that an even much larger collection of data did not. So if it didn't make that point to you, I have no choice but just to go on. So this turns out to be a pattern. It turns out to be a very general pattern. The theory takes care of it, and we don't need any of that detail. I wanted to show several things. Data is just data. It has this certain unintelligibility to it. Okay? There's something not satisfactory in our understanding when we're confronted with data and all we can make of it is that it's the data that it is. That's one of the primary drivers of inquiry, and I take it drivers of the intellectual. This is characteristically intellectual treatment of data. There are other things you could do, but what I did is I transformed the intelligibility by transforming the expressive usage, at least to the point where you could start to guess at a pattern, and then you could go on and eventually get to the Euler's level and formulate a claim, and eventually get to Gauss's level and prove a theorem. So that's what we're after. In perhaps more illuminating cases, but that's what we're after. But there are a few other remarks. From my point of view on intellectual understanding, the empirical, non-empirical distinction that some of you regard as rather central in epistemology is really a subsidiary matter. CERN buries us in data. Genetic analysis buries us in data. That's all empirical data. So the fact that my data each gets is just a simple arithmetic computation, well, it does change its empirical status. I'm not saying that it doesn't. But the feature that we're drawing out, that when data just sits there, there's a lack of a suboptimal state of understanding. That part, as well as I want to claim these fundamental aspects of the use of expressive means, are common to both cases. Our table is a periodicity detector. To find the Higgs, you need to use a detector too. Okay. Also, so the justificatory questions on quality of data are also seem to be, from this point of view, subsidiary. Not what epistemology is, but one of those important inquiries that we make in the context of epistemology. If the data is wrong, then that's also a problem. I agree. Okay. And then there's another point. Paradigmatically, thought confronts lack of insight. Philosophy of math since Frege has mostly focused on completed proofs. That has to do with the part 5 that we can't really get to. So some foundation. There's an obvious foundational issue. We tend to think notation, smotation. What part of New York City is that an expression from? Someone should know. It's been there. Anyhow, that, you can write things, notate something one way, you can notate it another way, get the same effect. That's been the general philosophical idea about notation. Well, it ain't always so. And so, of course, there's an insight there that it's possible to have many variant notations that do the same job. And if you're doing, philosophy of language and you only ever look at one language or sort of mature natural languages, maybe considering French as well as English, then, it looks like that's all there is to it. But we had a table that did a job that the listing couldn't do. And this, in the history of the intellectual, I claim is actually the typical situation where it matters. And so we abstract from the actual, we abstract the notion of a job as a functional role. That's a three-place relation. An expression plays a functional role in the usage where that expression is used. Other than that three-partness, it's a very similar abstraction as the one we deploy in the notion of proposition, which, however, tends to be used primarily monadically, though, of course, we're not incapable of saying that John said X, thereby expressing P in English. Okay. I claim this allows for forms of thought that may be distinctive in intellectual values, even if they solve shared problems, which is the handy case for making strict comparisons when they solve shared problems. So we had the listing and then the table from the same data. Okay? Well, my favorite case is Descartes' transformation of geometry. Descartes was very much concerned with solvability questions for ancient geometrical problems. Now, some of the stuff he did opened up new areas, and that is, to us, perhaps much more interesting. But the comparison, the sharp comparison can be made because he put very serious and elaborate effort into treatment of ancient style geometric problems. And he taught us how, given a geometric problem statement, to write out an algebraic equation. And there's no question that that is intellectually transformative. It's not that it, just because a language, just because it's algebra makes it easier, because, no, there were decades of delay in the reception of Descartes because nobody knew or wanted to learn the algebra. So historically, it isn't simply that you're writing it in a familiar language. No, Descartes was writing things in a familiar language, but it was decisive from the point of view of intelligibility for a variety of reasons. And I have spoken about that for many years on many occasions and don't want to go into the detail, but I need to list a couple of things. And so that case study is one that in appropriate places I will explain in detail. But when you write an equation, it gets a degree. No, you write the highest term x to the fourth, and there you have a quartic equation. There's something written there. There's an expressive means in that usage. that has no counterpart in ancient diagram-based thought. There isn't anything you can look at short of applying some transformation like Descartes does, which the ancients did not. And that's centuries worth, right? That's 1,000 years worth of ancients. That would tell you whether you're dealing with a quartic, that you're dealing with a quartic or a quintic problem. The other thing is that in a diagram, you have what I call coexact information, which is the sort of the topological, the combinatorial topology structure of the diagram. And that is what you actually can read off from the diagram in an ancient proof. And then you have exact information, which is stuff like line segments being equal, angles being equal, which you have to get from previous registration in the geometrical text. But the reason you have to use the diagram in the ancient form of thought, and you have to adduce this topological information. Once I've written equations, the topological information is actually gone. It's expressible in algebra. It takes algebraic inequalities, not equations. Descartes never writes algebraic inequalities. Now you might think, without that information, the original problem can't be solved. That's actually true. It just doesn't matter, because Descartes, by being able to separate it, is able to focus on the equality information and make the most of it. And that turns out to almost solve the problem, and Descartes knows when to go back and reinsert the diagram-based information to make a choice among finitely many solutions. So anyhow, there's a longer story that very clearly ties the change in expressive usage to the advances in systematicity and that Descartes is an understanding, theoretical perspective on ancient geometrical construction problems that Descartes obtains. Okay, so that was the second part. Part 3 remembers controlling your levels of detail, so that's what we're going to go into. And then there's part 4 on modularity, which I spoke about a few years ago, and so I'll be shorter on that. But there are in mathematical practice, there is a very wide diversity of intelligibility strategies that turn on exploiting special purpose expressive usages to control detail. This is urgent in mathematics because it needs to handle subtle issues with exceptional shareable precision and cogency. And whenever you're in a situation like that, you find that you have to give an enormous amount of detail, often much more detail than what you, intuitively speaking, really care about. So when I want to do the foundations of the theory of computability, I have to do them with Turing machines and say how many tapes and how the tape can move. Or there are a gazillion other ways in the 1930s and 40s that are developed to do this. And they all give me the same ultimate foundational results, but the proofs are completely different. And the proofs wouldn't work and wouldn't be cogent without attention to all this detail. You mathematize an intuitive topic, and all of a sudden, you're buried in detail, typically. Not necessarily, but typically. Okay? That's what I call overspecification. It's not what I want to know about computability, whether the Turing machine has one one-sided tape or 7 two-sided tapes, 3 of which are, only allow certain symbols. That's not what computability theory is about. Now, so sometimes there's a resolution in the computability theory case. The resolution is that once you have about 5 fundamental results, one comes to realize that you can argue for the rest entirely intuitively in computability theory, just invoking intuitive counterparts of those 5 fundamental results. This crystallized in Hartley Rogers' book called Recursion Theory in about 1960. And this is what has made higher recursion theory possible. So you can do that without any information. Once you've gotten the foundational results, you can do that without any information on the underlying computational model and its details. So that's a case of overcoming overspecification. Not completely, but in a certain phase of the operation, namely once you're done with the fundamental results, such as the existence of a universal Turing machine for any given number of inputs and Kleene reflection theorem. I'm not getting that quite right, but there are a few things that knowing that you can transfer control from one process to another and stuff like that. Okay. So mathematicians, the creative part of modern mathematics often is this finding an expressive usage that will allow you to proceed. Now, in the philosophy of physics, one might get a different impression. Your paradigmatic physics advance tends to be enhancing your observational resolution, sensitivity, or scope. Magnifying glasses, microscope, scanning, whatever microscope, right? Eyeglasses, telescope, Hubble, James Webb. It gets more exciting by the step. Cyclotrons in Berkeley, proton synchrotons at CERN, Hadron Collider, gravitational theory. I made this overhead for a talk in May, and so that's what I mean by last week. You know, when you look at nature and science, there's always going to be a couple of things that are the important advances of this type, okay, where you're getting more and better detail. And responsiveness enhancement has always gotten great press, and it fits well with the traditional epistemological view of you want to get things right and you need that detail. Very occasionally, so this is taken from Science 2009, you get somebody realizing that that less is more, that it's good to be able to discard details. You should look this up. There's a very pretty picture of it. Fibers in paper pictured under high magnification. And you say, look, I don't care. You know, when I want to make some notes on Manders' talk, I don't care about the internal, you know, the highly magnified internal structure of my paper. And something, and this is a common part of a commentary advertising, an article in that issue where someone gave some way of getting at entanglement without resolving, let's see, does it actually say here? Typically you get an entanglement via working out sort of all the details on the states involved, and somebody found a way of avoiding that. And in that connection, it was worth science's time to point out that there's this kind of advance too. This is my kind of advance. So I've pretty much introduced the topic here. On foundations of computability example, proof systems for first order logic. If you've ever taught logic, you know the students have to pay attention to exactly all the details of the proof system in the book, because if they don't, they're going to prove stuff that doesn't follow. It's guaranteed. But all the books are different. It isn't that the details are relevant to what you want to know directly. That is, well, relevant. That makes too much of a problem. In any case, you want to characterize, every book wants to characterize the same theorems. It's just that the approach to it requires this detail. I'm not convinced, but maybe someone can help me, that there's too great a resolution of this of the type that we have with the Rogers axioms in the foundations of computability. But that's no doubt a matter for dispute. There are going to be candidates. Here's another one of my favorite examples. Knot theory started in the late 19th century because I think it was Lord Kelvin thought that maybe you could explain how the elements work by assuming that there are different types of knots. Well, now we have string theory for that. That was Kelvin's version. Okay? And so he said, let's enumerate the types of knots. Now with knot, what we mean is there's two senses of knot that are intuitively relevant. Okay? The one is when I actually have this thing arranged in space. The other is the sense in which I have the same knot individuated differently, namely the sense in which when I drop it on the floor, it's still the same knot if nothing broke. Okay? And the sense Kelvin and everybody wants is that sense of same knot. But the only ways we have of presenting knots threaten to be of the first type, and that's your overspecification problem. And I have said in front of the knot theorists at Cambridge University that the point of knot theory has always been to overcome that overspecification problem. Not that they don't do lots of it, and they were happy with that. Maybe not the graduate students, but the senior faculty. Okay? So there's lots of interesting stuff going on in knot theory that does not directly relate to this, but the senior people recognize that the real theme in knot theory is getting at the knot types. Now, if I mathematize this notion of knot, it becomes a 1-1 continuous map of the circle into the 3-ball. Actually, there's some other specifications you make for technical reasons. Won't work unless you specify some further choices, but that's not relevant to what we're saying now. Well, so I have a circle, and now if I give you a map, I'm telling you where each point of the circle goes in this knot. Of course, I could monotonically shift this on the circle. I'd have the same knot, intuitively speaking, but the mathematical object under ordinary individuation is a different one. So, right, and that's even before I drop the knot. And it still has the same type. So mathematizing it makes it so much worse. And again, I don't care about the coordinates. You know, I could lower the knot by 1 inch. All the coordinates different. Certainly, if I drop the knot on the floor, the coordinates no longer have the relationships, you know, the various quantitative relationships between each other that they did before. So all that, from the point of view of wanting to know what the finite knot types are, is in some sense irrelevant, but we don't have another way of giving them. Okay. Well, before we had this definition of knot, we had knot diagrams. Basically, people who worked with nets had the way of seeing knots that goes into knot diagrams, and all of a sudden we've reduced it to finite information that still determines the knot type, but it still over-determines the knot type and is in fact not decidable whether two diagrams, at any rate, not known to be decidable, probably not known to be undecidable either, whether two knot diagrams give the same knot type, even though we know that if they do give the same knot type, then they can be connected by a simple series of transformations, and otherwise they can't. But that's not good enough. So at that point, you're driven to look at invariants. These are features that can be attributed to the knot and indeed can be attributed to the knot type, but do not by themselves completely characterize that type. That is, different types will share these features. But the more of these features you have, the better chances you have of being able to tell. So you get the same Alexander or Humphrey polynomial from a knot. You don't know that it has the same knot type, though chances are pretty good. There's more there. So many advances in intelligibility arise by deploying expressive means that allow you to reduce detail without losing ability to advance on the questions you really care about. So the knot diagrams are the simplest and most easily explained. Striking example of that. You take a discipline such as topology. You have a topological space, and now if you describe with mathematical precision your topological space to me, then you've told me an infinite amount of stuff that no topologist wants to know. What we care about if we're doing topology is what properties of that thing are shared by all quote-unquote homeomorphic spaces. That's just the technical term for being invertibly mappable by a continuous map. So, in the early 20th century, one learned to recognize and compute algebraic invariants. And you get things called the homotopy groups and the homology groups. And the typical output of this is where I say this group has 5 generators. And here are 6 combinations of those generators that give you the unit element of the group. That's called generators and relations. And so you've got a very small expressive package that tells you that group, and if the group is different, then the space must be different. Unfortunately, a group has many such descriptions, and it's known to be undecidable whether any 2 such finite descriptions are of the same group, when it's an isomorphic group. Oh, you've enormously reduced the overspecification, but you're still stuck with it. And so then there's this area called combinatorial group theory, where we try and extract actual properties of the group from the generators and relation information and study these questions on how hard it is to tell whether two specifications of that type of a group are actually specifying isomorphic groups. And then around 1980, we got a whole new approach to this that said, look at the Cayley graph of the group. That's determined by the generators. That's just, you got points for the group elements and arrows if multiplying that element by A takes me to this other point, then I'd put in an arrow labeled A, where A is one of the generators. So that's the Cayley graph. And of course, it depends still on these generators. And so it's an overspecification. But once you've put it in that form, there's something you can do. Namely, you can look at that graph with those connections as a metric space, and you can look at it up to what's called quasi-isometry. And lo and behold, the quasi-isometry type of a group no longer depends on the choice of generators and relations. On the other hand, it lets in other groups and it lets in other spaces that don't come from groups. That turns out to be another advantage because they're Riemannian spaces in which independently a large theory exists. And so you find results in Riemannian spaces telling you things about these groups and vice versa. Okay. So here, Gromov's notion of quasi-isometry suppresses the overspecification that remains, but at certain costs. So this is not an abstractive move. You're not having less information. Metric spaces count as more highly structured than Cayley graphs normally count as, because you don't normally look at them as geometries, but just as graphs. And more highly structured, certainly, than groups given abstractly by generators and relations. This isn't an abstractive type of move, but by using different expressive means, you can make new features available. Here's another example of that same phenomenon. I need to tell you just a bit of background on finite groups. We like finite groups. Simple groups are ones that you can only map to itself and to one, or you have to injure a group multiplication in the image. Right, so if you don't image, this is preserving the group multiplication. Bernstein in 1897, having looked at a lot of examples, said that the only finite simple groups of odd order are the prime cyclics. So the cycle of 3, permutating 3 pennies cyclically. You cannot permute them one stretch, or permute them twice, which is the same, gives the same effect as permuting them one step in the other direction. You give your pennies arranged in a circle. Yes, you get a 3-element group there. That's a simple group. There's no way of preserving the composition of your rotations and mapping that to a 2-element group. It has to be the 3-element group, or everything trivial, the 1-element group. Okay. Well, so in 1963, sort of an earthquake-level event in finite group theory occurred when this was proved. And it goes way beyond existing theory. And Jeremy will set me right on this. But the general character, there are few general interest intermediate results. There are a couple of name theorems in the first part that Jeremy has computerized. But basically, you're just hacking away. awful. So people have been trying to rewrite that. Part A was rewritten in a book. Part B is this character theory I'm going to be telling you about, and it seems indispensable there. And without this, you couldn't get started on the classification of the finite simple groups. Okay. I want to point out that so far, I have said nothing about the nature of group elements. I've just talked about group elements and composition and mappings. And there are many things that the group elements could be, and they could be transformation groups, or they can be these groups that arise in topology, where you're composing paths in your space and stuff like that. Matrices. But let me tell you a little bit about matrix groups. So physics undergraduates are taught how to multiply matrices, especially 2 by 2 and 3 by 3, right? And so here I've taken the group of permutations on 3 items. There's 6 of them. I can leave 1 where it is, 2 where it is, and 3 where it is. It's the identity element. I can leave 1 alone, but permute 2 and 3, and so on. Or I can do the 2 cyclic permutations. That gives me 6 things. I can mimic that. I can get that behavior in the multiplication of these 6 matrices, respectively. Think of this in columns. This is the identity matrix. These are the 3 matrices of order 2. These are 2 matrices of order 3. And these 2 and this one form the 3-element cyclic group. And all of them together, they form S3. And I've verified some computations for you. And there are infinitely many equivalent representations with different matrix entries. Each one, of course, overspecifies S3, therefore, enormously. We just don't care what these entries are. Now, typically, there aren't any zeros, and you get all kinds of weird numbers there. That's an equally good matrix representation of the symmetric group on 3 elements. Okay. But they have some invariants. All these representations share certain features, namely the coefficients of the characteristic polynomial, and in 2 dimensions, that's the determinant and the trace. And just by looking at the determinant, I can see something group theoretical, namely that the group is not simple. Because when some of them have determinant 1 and some others don't, when more than one of them has determinant 1 and some others don't, then I already know that the group is not simple. No matter what matrices I use to represent this group, as long as they have the right multiplication among them, I will find these values for the determinant. And then there's the trace, which is the sum of the diagonal elements, also the sum of the eigenvalues for you physicists. Okay, such spectral properties lack counterparts in abstract group usage. There are all kinds of properties of these sums of diagonals in particular, and the function that they form when I do it for each of these. So this function here, 2, 0, 0, minus 1, 0, minus 1, minus 1, that's called the character of this representation. And these are simply numerical things. They don't live in the group. They don't talk the group's language. But we can use them to get at features of the group that we are unable to get at in the ordinary language of group theory, composition, subgroups, congruence relations, and mappings, homomorphisms, and so on. All the works don't allow you to get at these features that you seem to need to prove the odd order theorem. So people have been trying to simplify this proof And 2 different books have appeared on that for different parts, but no one is anywhere near eliminating this. So here what we do is we leave our abstract usage from where the problem was posed. That's what we care about. No simple groups of odd order except the trivial abelian ones. We leave that. We go to this overspecification of the group, where we say all this stuff in detail about the group elements, though we don't care about it one bit. But from that, we're able to reduce the detail differently, namely by these functions, and extract invariants of the original group, not just features of the representation, but things that, because all representations share them, we can attribute them to the original group that allow the proofs to proceed. Okay. This kind of thing happens in mathematics over and over again, and it is not abstractive, and it is the art of deploying various expressive means to bring out features by various types of control of detail. Okay. A lot of what works for Descartes is the fact that his method has 6 or 8 different stages, and at different stages you require lesser information, though, or that information is only available if you have Descartes' expressive means. They make it possible for there to be subsets of the information expressed that allow you to do the job of that particular step and then get back to the overall project. I don't want to go into that in detail. This allows you to split arguments into lemmas and intermediate results. We already know that from Euclid. It's very useful in Euclid. There the informational aspect is that the construction lines of my lemma's proof do not reappear in the diagram of the theorem I'm proving when I invoke the lemma, and otherwise diagrams would be unmanageable and couldn't fulfill their expressive roles in ancient geometrical thought. In knot theory, we reduced from the knot as mapping to enumerating knot diagrams, so that was already done in the 19th century, though with computers we can get a little further. And then you can go to topology of what's called the knot complement, which is what's left of the ball when I take the knot thought of having a little bit of thickness out. Then I have this ball missing something, and that's the knot complement. And it's, I think, mid or late 1980s result that the topological features of the knot complement, the total topology of the knot complement, not that we can enumerate what all the relevant features are, but the total topology of the knot complement does determine the knot type. And mostly what we have are these topological invariants that I mentioned before. They give me some information on the knot type, the same type, then certainly the same invariant, but the same invariant might not imply the same type. So there's that strategy I've discussed in algebraic topology. I've discussed it in Descartes' case. So one of the things one does to enhance intelligibility is splitting things up into stages where specialized methods can use. And this has non-trivial expressive resource requirements. So, when we think about building a building, you say, okay, so we have the architect and we employ less skilled people for the rest. But frankly, the architect probably can't operate the heavy machinery, so the less skilled is not entirely on point. Hey, I'll send that one to Trump, tweet that to Trump. To be able to decompose into sub-projects and put the results effectively together towards your overall goal again poses significant requirements on expressive means, and typically you have to come up with expressive means as part of the process of coming up with the modularization in the substages. Expressive means that we're using don't necessarily support a decomposition. When I take an ordinary photograph, I'm not talking about the ones that get bought by museums, but when we take an ordinary photograph, it shows everything. You go look at this, and you on the website when they put this talk up, and you will see what color sweater I had on, even though that's not perhaps what you were looking for, and I don't encourage you to look for it. But it's all there. It's up to you to pick out what you want to look at. The expressive means do not help highlighting anything. In geometrical diagram reasoning, you can't just separate parts of the diagram. And I can't have my triangle here and then and need to enter my line dB and put dB over here, because then, you know, the items don't interact, and I don't get the topological information that the proof is going to require. That's 1.6. Forecasting the weather, it's very hard to take that apart. If you believe this butterfly effect thing, which is, of course, an exaggeration, fluttering of one butterfly in the Azores will change the weather here next week. Well, so that is an exaggeration, but to the extent that that were true, you would have an indecomposability unless you find other ways of expressing relevant information that allow you to do separate pieces of your weather prediction computation on separate supercomputers. Those of you who know Tolkien will know what I meant. Okay, then there's this topic 5. Chief among expressive functional roles is providing facilities for finding answers. That is a morass. There are a bunch of interesting things to be said about it. On we go. Maybe on some future occasion, if I ever get the courage. Okay. So I claim expressive usages. If you watch expressive usages, you get something that you as a philosopher can talk about. Comparisons of functional roles and effects of of expressive usages. That has real explanatory value in seeing why certain intellectual maneuvers enhance intelligibility. And in this way, distinct expressive uses, even ones solving the same set of problems, can make distinctive functional roles available and have distinctive intelligibility impacts. In Descartes' case, there are some things that are better with ancient diagrams. Bothered Leibniz for all his life. There are some things that are better in the algebra. I'm going to skip this. There's a bit of background theory that we didn't have time for. And as I'm over time, I want just maybe to advertise a line of thought here that can take off from here. The point is that if you look at what, say, my table did, it highlights certain features of relationships. That means it's providing a facility that enables me to attend to those features. Now, there's been a fundamental divide, I think, in modern philosophy that shows up with Frege's Sinn and reference. Frege would never have used such terminology as attention, but if you go back and read, you'll see that his examples, his use of the term thought, etc., in the context of Sinn, are in fact what's involved are intention control mechanism roles of expressive means. It is the mode of presentation, remember. Okay? Well, the mode of presentation is what we can respond to. Okay? And so, fundamental philosophy in the English-speaking 20th century has gone very heavily on the referential side. And we've not found philosophical ways of dealing with phenomena of attention control, but that's the kind of thing that I think my considerations on expressive usage are actually supplying. Thank you very much.